Hi everyone, I welcome all of you in this session. I hope all of you are well. So dear children, as you know that our topic is similar triangles, and in earlier video we have discussed the basic proportionality theorem and corollary of a basic proportionality theorem. Now today we are going to discuss about the topic converse of basic proportionality theorem. But before discussing the converse of basic proportionality theorem, I would like to recapitulate the basic proportionality theorem. Basic proportionality theorem is, if we have a triangle and if a line parallel to one side of a triangle, then it intersects the other two sides at two distinct points, then the line divides the two sides of a triangle in the same ratio. And we have proved this result in previous lecture. Now today we are going to discuss its converse of basic proportionality theorem. So converse of basic proportionality theorem. First of all, let us understand the statement of basic proportionality theorem. The statement is, if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. So first of all, we have a triangle here. ABC is a triangle. Let it be A, B and C. ABC is a triangle, a line which divides any two sides of a triangle in the same ratio. Let the line be here, this one, and we can write this as D and this point as E here. So it is given in the theorem that this line DE divides the side AB and a side AC in the same ratio. Then what we are going to prove here, show that this DE is parallel to the side BC. First of all, given is given in triangle ABC, in triangle ABC, line DE is parallel to line DE divides, or we can say that line DE intersects AB and AC. In triangle ABC, line DE intersects AB and DC at D and E respectively. Then, so this line DE divides AB and AC at point D and E such that it divides the side AD by DB is equal to AE upon EC. This is given in the statement of converse of basic proportionality theorem. A line divides the two sides in the same ratio, that is AD by DB is equal to AE by EC. Then to prove, what we have to prove here, to prove this DE is parallel to the side BC. We have to show here DE line is parallel to BC. Now construction here. Construction is, if possible, suppose DE is not parallel to the side BC here, we can write here, if possible, let DE is not parallel to BC. Then draw another line. We can write here, draw DF. Draw a line DF parallel to BC. Like this DF this is DF line parallel to BC by construction. Now, by basic proportionality theorem, if we have a triangle ABC and we have any line parallel to one of its side, so here by construction we suppose this DF is parallel to BC line. For this triangle we can use now basic proportionality theorem. Now let us take proof here. Proof is, in triangle ABC, which line is parallel here by construction? DF is parallel to BC by construction. DF is parallel to BC. So by basic proportionality theorem, this DF intersects the two sides AB and AC at two distinct points, that is D and F. So by basic proportionality theorem, this DF line divides the two sides in the same ratio. So we can write AD by DB is equivalent to AF by FC. We call this as 1, and the reason is by basic proportionality theorem. By basic proportionality theorem. So we take triangle ABC in which we have DF is parallel to BC by construction, and we apply here basic proportionality theorem. We can write AD by DB is equivalent to AF by FC. We call this as 1, and the reason is by basic proportionality theorem. But what is the given condition here? Given is AD divided by DB is equivalent to AE by EC. We can write here AD, but this AD by DB is equivalent to, by the given condition, AE by EC, and we call this as second one. It is given. But when we compare the two equations, equation 1 here and a second equation here, we observe on comparing both the two, we observe here that the left hand sides of both the equation 1 and equation 2 are equal. Left hand side of the first one is AD divided by DB, and the left hand side of the second one is also AD divided by DB. On comparing the two, or we can write it as from first and second, we get their right hand sides are equal. The right hand side of first is AF by FC is equivalent to right hand side of the second equation. So the right hand side of the second equation is AE upon EC. Now we have to show that here this DE is parallel to BC. Now we have here AF by FC and AE by EC. If we take one step again here, AF by FC plus 1. We add 1 to LHS and same add 1 to RHS here. It equivalent to AE by EC plus 1. So we can write here adding 1 on both sides. Adding 1 on both sides. If we multiple here the two, AF by FC plus 1, we can write it here. It implies we have AF plus FC divided by FC. This one, AF1 into FC is FC and divided by FC is equivalent to same here, that is AE plus 1 divided by EC. So we can write it as AE plus this EC divided by EC. Look at the figure and this one. What about AF plus FC? If we observe the figure here, AF plus FC. Yes, what will be AF plus FC? It equals to AC. Exactly. It implies we can write here it is AC divided by FC. Similarly, from the other side of the equation, that is AE plus EC. Once again, look at the figure. What about AE plus EC? We can write AC. So it is also AC upon, this is AC by EC. If we observe the two, we observe here both the numerators are equal here. It is AC and AC. Further, we can write it as, it implies 1 upon FC is equivalent to 1 upon EC, because AC and AC are same. In both the numerators, we can cancel out the two. So we get here 1 upon FC is equivalent to 1 upon EC. If we take reciprocal on both sides, we get here FC upon EC. Once again, look at the figure, look at the diagram. This is FC is equivalent to EC. Is it geometrically possible this FC is equivalent to EC? This FC is equivalent to EC. Is it geometrically possible here? No, it is possible only when point F coincides with point E. So here we can write FC is equal to EC is not possible. So this is possible only. We can write here this is possible. This is possible if, or this is possible when E and F coincide. So this is possible. FC is not equals to EC. It is possible only when point F coincides with point E. It means F and E are not two distinct points but they same. So when point E and point F coincides with one another, hence we can write, hence this DE is parallel to the third side BC of a triangle. So on the basis of these two results, that is basic proportionality theorem and converse of a basic proportionality theorem, let us take some examples based on this basic proportionality theorem and converse of basic proportionality theorem. Take a first example, example 1. Example 1. Consider a triangle ABC If we have a triangle ABC, this is A here, this is B, and this one is C. There is a line DE which is parallel to one of its side. Let the line be here, this one. This is DE, D and E. And this DE divides the two sides in some ratio, that is AD and DB. It is also given here the length from A to D is 1.5 centimeter. The length from D to B is 3 centimeter. The length from A to E is 1 centimeter. And the question is how to find out the ratio, how to find out the segment of CE. This is question mark here. We have to find out this EC. So the question is triangle ABC, a line DE is given parallel to one of its side BC, and the segment of A to D is 1.5, D to B is 3, A to E is 1 centimeter, and we have to find EC. So what is given here? We can write here first of all in this example given is DE, or we can write in triangle ABC. DE is parallel to side BC. This is given. Then to find, we have to find here, that is EC. We have to find EC. So which theorem we have to use here? Simply we have a triangle ABC and one line, that is DE, is given parallel to one side of a triangle, that is BC. Clearly we use basic proportionality theorem here. So solution is, we can write it as solution, that is in triangle ABC, in triangle ABC, this DE is parallel to BC. By basic proportionality theorem, we can write here, that is AD upon DB. So AD upon DB is equivalent to AE upon EC. So reason is by basic proportionality theorem. So out of the 4 segments, 3 is known to us. One is A to D, that equals to 1.5. We can write it as 1.5 centimeter. This, and D to B is given 3 centimeter. Simply A to E is 1 centimeter. And this E to C is to find, we can write same it as EC or CE. So here when we multiply the two, can we write it as 1.5 upon 3 is equivalent to 0.5? After cancelling 1.5 and 3, it is 0.5 is equivalent to 1 centimeter upon EC. Then simply we can write here EC is equivalent to, it is 1 divided by 0.5, or you can simply write it equals to 2 centimeter. So the length of this segment 2C is equal to here, this is 2 centimeter. So here we use basic proportionality theorem. Why? We have a given triangle ABC and one line is parallel DE. It intersects the two sides at 2 points, and there are some segment is given, that is AD 1.5, BD 3 centimeter, AE 1 centimeter, and we have to find the segment E to C. By using the basic proportionality theorem here, we find this, the length EC is equal to here 2 centimeter. Now let us take another example, example number 2. Example 2. So this is based on the basic proportionality theorem. Now we take another example based on converse of basic proportionality theorem. Consider a triangle PQR. Let this one be a triangle PQR. This is P, Q and R triangle. Call it as P, Q and R triangle. And there are 2 points, one on PQ side and other on PR side. Let the 2 points be E and F here. Let it be E and this one be F. The question is, if we join E and F, this line, and it divides the two sides in some ratio, in some segments, that is PE, EQ, PF and FR. If PE is equivalent to 3.9 centimeter, if it is given 3.9 centimeter, and EQ is equal to 3 centimeter, this is 3 centimeter. Then again PF is given, it is 3.6 centimeter. Then another segment, that is FR, it equals to 2.4 centimeter. Here observe the figure keenly. We have here 4 segments, that is PE, EQ, PF and FR. All the 4 segments are here given. But what we have to prove, show that this EF is parallel to QR. We use here converse of the basic proportionality theorem, because we have learned this converse of basic proportionality theorem. If a line divides two sides of a triangle in the same ratio, then the line is parallel to the third side. So here, first of all, look, we have to here check whether this point E divides P and Q and F divides F and R in the same ratio. If they divide in the same ratio, then this line EF is parallel to the third side, otherwise it is not parallel to the third side. So here we have, in this one we can write solution same, PE by EQ is equal to 3.9 centimeter upon 3 centimeter. Further, it implies here PE by EQ is equivalent to 3.9 upon 3. When you cancel out, it becomes 1.3 centimeter. Is the ratio between PE and EQ. Now let us take another one, PF by FR. Here the length from P to F is 3.6 centimeter and FR is 2.4 centimeter. Now we can write further it as PF by FR is equivalent to, can we write it as 36 upon 24? Yes, we can write it as 36 upon 24. Whenever we cancel out the two, we get here PF by FR. Here cancellation is possible, that is 12 2 or 24 and 12 3 or 36. We get 3 upon 2. So when we divide 3 upon 2, we get here 3 upon 2 is 1.5 centimeter. Now look here, PE by EQ is equal to 1 upon 3, this one, and here PF by FR is equal to 1.3. Can we say that here P and EQ 1.3 and PF by FR is equal to 1.5? They are definitely not equal to one another. So we can write here, therefore PE by EQ is not equal to, you can write here like this, is not equal to PF by FR. It means this line EF is not dividing the two sides PQ and PR of a triangle PQR in the same ratio. When the line is not dividing the two sides in the same ratio, hence we can write here, hence this EF is not parallel, this is parallel and this means not parallel to the line segment QR. So now let us take example number 3rd on the basis of these two theorems, that is basic proportionality theorem and converse of the basic proportionality theorem. So example 3rd. Example number 3. The question is PQR is a triangle like this. This is P, QR is a triangle in which there is a point in its interior, that is point O here, and if we join this P to O, further if we join this O to Q and this one O to R, and there is a point D on side PO, this is point D here. The information is given in the question, PQR is a triangle, DE is parallel to OQ. This is DE. It is given in the question that this DE is parallel to OQ and another one DF like this is parallel to another side, that is OR. Then what we are going to here prove, show that this EF, when we join this E and F, we have to show that this EF is parallel to the third side QR of a triangle. First of all, look at the given condition here. We have a triangle PQR in which one line, that is one line segment DE, is parallel to OQ and another line DF is parallel to OR. Then we have to show that in this question that EF is parallel to QR. First of all, given condition is, what is given here? So the given is here, this is given. A triangle PQR DE is parallel to, this DE is parallel to OQ. This is parallel to OQ. DF, another one here, DF is parallel to OR. Is parallel to OR. This is given condition. Then to prove, we have to show that this EF line is parallel to the QR side of a triangle PQR. Yes, we have to show that this line is parallel to QR. We know by the converse of basic proportionality theorem, if a line divides the two sides of a triangle in the same ratio, here we have a line EF. We have to show that this EF divides the side PQ, means PE and EQ, and the other side PR, that is PF by FR. If we prove this, PE by EQ is equivalent to PF by FR, then we can say that the line PEF is parallel to the third side QR. So let us take proof of this question. So which line is parallel to one side of the triangle here? So here it is given, this DE is parallel to OQ. So which triangle we are supposed to take here? So we have to take triangle POQ. Why we take this triangle out of these triangles? Because in this POQ triangle we have a one line, that is DE, which is parallel to the side O and Q. So we take the triangle POQ. In triangle POQ, DE is parallel to the side OQ. So we use here which theorem? Basic proportionality theorem. Excellent. So by basic proportionality theorem we can write PE by this PE upon EQ is equivalent to, yes, PD by DO. Very good. It is PD by DO. The reason is, we call this as equation 1 and we can reason right here the reason by basic proportionality theorem. So in triangle POQ, DE is parallel to OQ and we use basic proportionality theorem. PE by EQ is equal to PD by DO. Now let us take another triangle and we take the triangle here POR. Why we take this triangle again? Because this DF line is parallel to QR, OR side of the triangle POR. So let us take this triangle again. In triangle POR, here we have a triangle POR again from this triangle POR. Which line is parallel? Definitely DF. Here DF is parallel to the side OR of this triangle. So again we are using here basic proportionality theorem. Therefore we can write PF by FR is equivalent to PD by DO. Very good. This is second one. Reason is same, by basic proportionality theorem. Observe the two equations that we have written here, that is equation 1 and equation 2. If we observe the two equations, you observe that the right hand side of first is PD divided by DO is equal to the right hand side of the second, that is PD divided by DO. We know that when things which are equal to the same thing, they are equals to one another. On comparing 1 and 2, so we can write here from 1 and 2. We get, so on comparing the two, their right hand sides are equal, so we can write their left hand side, that is this PE by EQ is equal to PF by FR. PF by FR, this is PF upon FR. So here on comparing the two, we get their left hand side, that is PE by EQ is equal to PF by FR. So consider again a triangle PQR. We have proved here that the segment PE by EQ is equal to PF by FR. Definitely this line EF divides the two sides PQ and PR of a triangle PQR in the same ratio here. So by converse of basic proportionality theorem, we can write here by converse means C of basic proportionality theorem. In short, we can write as CBPT means converse of basic proportionality theorem. This line EF is parallel to the third side QR of a triangle PQ and R. So dear children, this is all for today. I hope you understood all that we have discussed so far. We'll meet you again in the next session. Till then, take care of yourself.